All right, so this section is pretty much going to be mostly a review. You should know how to do all of this already, but we'll just be going over it one more time. So basically, looking at the title, all we're doing is going to be comparing and describing two different functions, exponential and linear functions, based on a table, based on a graph. You're going to use you're going to use both different types to answer a word problem. So let's get right into it. Your objectives. Describe the difference between the way values of two tables change and be able to determine the type of function based on the changes. Use given information to construct functions to solve real world examples. And finally, describe the type of function based on a graph. That's the easiest one. All right, so let's start with the first one, describing and explaining the difference in two functions. So if you're given a problem, two tables, and asked to describe the difference in the rate of change between the two, name the functions, and explain how you knew. Here's what you would do. So first thing, determine the rate of change between the two functions. So in other words, what's going on in this table, and you're only looking at the f of x or y column, depending on what the particular table you have is. And in this case, so between 4 and 9, we're adding 5. Between 9 and 14, we're adding 5. And if you look, we're adding 5 each time. Okay, go to the second one. Between 1 and 4, we're adding 3, but between 4 and 16, we're not adding 3. So since we're not adding the same amount, this isn't a linear function, which means that we're doing something else each time. So how else can you get 4 from 1? Well, you can multiply it by 4. And then if you do 4 times 4, you're going to get 16, and 16 times 4 is 64, and so on and so forth. So here we have multiplication each time. Multiplication or division each time you know means exponential. Addition or subtraction each time you should know means linear. So table 1 has a rate of change of plus 5. Table 2 has a rate of change of multiples of 5. Not 5. That should be 4. 4. And second question, determine the type of function. Well, we know table 1 is linear increasing because it's going up each time. We know that table 2 is exponential growth because the numbers are getting bigger and we're multiplying each time. That's not always going to be the case, so pay attention to what's in the tables. And how did you know? Well, we know because of what we just said. In table 1, as x increases by 1, f of x increases by a constant amount. For table 2, we knew it was exponential because as x increases by 1, the f of x increased by a multiple of 4 rather than just increasing by a constant amount. So that's how you would know, that's what you would write down, because you've got to make sure you have all three of these components to your answer. So I only showed two, I discussed the third. But in the example, you'll see it written down, kind of how I want it. Okay, next. We have a real world example. So as part of his biology project, Dan is observing the growth of two plants. Plant A had an original height of 8 inches and is growing at 2.5 inches per week. Plant B had an original height of 4 inches and its height is increasing by 45% each week. So first we have to write a function for that represents the growth of each plant. Well, if you look at the first part, just part A, because if we go back, there's a part B too, about how long will it take for plant B to reach the same height as plant A, and how tall will the plants be at the time. So let's focus on the first part, writing the function. So plant A, that's growing a rate of plus 2.5 inches per week, meaning every week we add 2.5 inches. So that tells us that it's linear, so we're going to use slope-intercept form. You know, f of x equals mx plus b, where m is the rate of change and b is the y-intercept. So we're going to put that 2.5 in for m, and the y-intercept is the initial starting height. So here's the 2.5, here's the 8. Okay, that's your y-intercept right there. So y-intercept, or we'll also put, for the sake of this problem, starting height. Okay, so we have one function now, so you should also write this as f of x. So we'll cross that out and put f of x. Okay, now for the second plant, we're growing a rate of times 1.45 inches per week. And we know that because anytime you see a percent increase, we're talking about exponential. So you always take 1, and then if it's exponential growth, you add whatever your rate is, in this case 0.45, If it was exponential decay, you would subtract 0.45. So we know that's our rate of change, so we write as an exponential function. Y equals I times 1 plus r to the x power, where I is the starting height and that 1 plus r is the rate of change. So we plug that in. The starting height was 4. Okay, so we put that in there for the starting height. And the rate of change we said was 45%, which translates to 0.45. So 1 plus 0.45 equals 1.45 to the x power. So now we have our equations, and you could take, and what you will do is you will take and you'll plug those into your calculators. You'll have to plug in two separate functions and then graph it. And when you graph it, it'll look something like this. Obviously not quite the same, but your graph will have those lines. All right, so to find the point where they're both going to be the same height at the same time, you need to find the point of intersection, which, let me change the color here. Let's change it to black. So that point of intersection is right there, okay, where the two lines cross. All right, so I'll show you how to do it in class. Don't worry. There's a function on your calculators to find the intersection. And for this particular graph, that point is at 4.08, 18.2, and that's just kind of an estimate because we're going to round to the nearest tenth or hundredth, whatever. And so that means, because this over here, this is the height of the plant, and this is the time in weeks. All right, so that means, now if this is our x value, that means it's going to take, after 4.08 weeks, we should be specific. Plants are going to be the same height at 18.2 inches, okay? And then last but not least, I'm really not going to waste a whole lot of time on this because you've seen this 3 or 4 times already. So describe the function based on the type of graph. In other words, what I'm asking is, what type of function is this? Is it linear? Is it exponential? Is it quadratic? Does it have is it exponential growth or decay? Is it linear increasing or decreasing? Is it quadratic with a minimum or maximum? In this case, we have an exponential function. From left to right, it is going up. So if it only has that one curve, it's exponential. And since it's going up, it's exponential growth. Here we have a straight line, which tells us it's linear. And since from left to right it's going down, it's linear decreasing. Easy enough. All right, let's take a look at some examples. Now, what I want you to do with these is look at the example and pause it. Try to do the problem on your own. If you get stuck, that's fine. But you're really not going to learn anything if all you're doing is writing down everything that I do. So try and do the problem on your own and then play the video and see if you got it right. And if not, hopefully you can look and see what you did. All right, so example 1, given 2 tables, describe the difference in the rate of change between the two. Name the functions and explain how you knew. So this is where you would pause it. All right, so first things first, rate of change, difference in the rate of change. Well, table 1 has a rate of change of, we're dividing by 5, okay? Dividing by 5 each time. All right, or you could say, the alternative to this would be, or multiplying by 1/5. Up to you. Second tables, this is going up plus 1 for every 1 this goes up. So plus 1, plus 1, plus 1. So it has a rate of change of plus 1. The functions, since we're dividing, that means it's decay, exponential decay. Okay, remember, multiplication or division is exponential. Division is decay, multiplication is growth. So since we're dividing, it's exponential decay. Second one's linear growth because as x goes up, so does y. If y was going down as x goes up, then it would be linear decreasing, and this should be increasing if we're being exact. Okay? And we know this because an exponential function changes by multiplying or dividing by a constant number, and a linear function changes by adding or subtracting a constant number. So that's what I would be looking for in the third part of the answer. So in this case, we knew it because we knew it was an exponential function because we were dividing by a constant number, which in this case was 5. And a linear function changes by, we were adding, not subtracting for this one, by a constant number, which was 1. So again, hopefully you kind of have an idea as to what I'm looking for now. Example 2, okay. So as part of her biology project, Holly is observing the growth of 2 plants. Plant A had an original height of 7 inches and is growing 2 inches per week. Plant B had an original height of 5 inches and its height is increasing by 35% each week. So first things first, write a function. Plant A, okay, we're adding 2 inches each week. So this is again linear increasing. So we write f of x equals 2, because that's how much it's increasing by. That's the rate of change, plus 7, because that is the y-intercept or the initial height, depending on how you want to look at it. Plant B, okay, remember initial height is 5. Okay, so that goes right there, and then it's increasing by 35%. So 1 plus 0.35, then just to the x power. So unless we have a graphing calculator at home, you're not going to be able to do this one. But if you did and you found the point of intersection, they would both be 13.7 inches after 3.4 weeks. So that answer is more exact than the last one, which is what I'm looking for. Okay? Last example. Describe the type of functions from the graph below. Again, we've got this one curve here. Okay, so this is exponential because it's not a straight line and it's not going back up. So it's exponential. And since it's from left to right, it's going down, it's exponential decay. Here we have a straight line, and from left to right, it goes up. So it's linear increasing. All right, so that is Unit 9. We are done. I have some suggestions for the test, and I would beg you to take them to heart. So I would go back and look at the examples shown in each of the videos. Make sure you understand how to do those. If you have questions, you need to see me before or after school. Okay, during class, we're not going to be able to do that this week. Well, you might have a little bit of time on Thursday, but for the most part, this is going to be a full week. So you need to do it before or after school. And please don't wait till the night before to study. That really doesn't work. You might think it does, but yeah, not so much. All right. Have a good one, guys. We are in the home stretch now. It is almost the end of the year. So I've been, for the most part, very proud of how you guys have done with these videos, finishing up the year. So keep it up. One more unit to go. You can do it. All right. Take it easy.